Hello everyone. Again, we'll start with the lecture related to the expectation value of expectation values of dynamical variables. So this is a part of paper 9 semester 4 physics honors. So we'll consider actually basically what you should understand that any physical quantity which can be experimentally measured is referred to as the physical observable or observable simply, and they are also known as dynamical variable. Now this, for example, you can take a physical observable. The example will be, say, position or momentum. Okay, position, momentum, energy are all observable. So basically these are the physical quantities, okay, and it can be experimentally measured. Now we are talking about the expectation values of dynamical variables. So we'll consider okay, a number of particles rather, okay, distributed along the x-axis, as there are n1 particles at x1, similarly n2 particles at x2, and so on. So the average position of number of particles, okay, would be given by x bar equal to n1 x1 plus n2 x2 plus dot 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 divided by n1 plus n2 plus n3 and so on. So this is the average position of the number of particles, okay, that is what we have to remember. So this could be written in summation form, summation and subscript I, x subscript I, okay, summation I and subscript I. So this could be written in this way. So in quantum mechanics, where a behavior of a single particle is involved, okay, we calculate expectation value, okay, which is denoted by this of the position. This is the expectation value of the expectation. This is the expectation value of the position of particle confined to the x-axis, okay, and that is described by the wave function psi x comma t. In this case, we can replace the number ni of particles at xi by probability p subscript I. So here this could be replaced by p subscript I, okay, and that the particle be found in an interval, okay, in an interval dx at x subscript I. So the probability p subscript I will be given by psi I asterisk into psi I dx, which is equal to psi I mod of psi I square dx, where psi subscript I, this is the particle wave function at x equal to x subscript I. Now making this substitution, okay, and changing the summation, okay, in equation 1. So we'll consider this one to be equation 1, okay. In equation 1, into integrations, we find the expectation value of the position of the single particle is, it could be written like this, minus infinity to plus infinity psi asterisk x psi dx by, again, minus infinity to infinity psi asterisk into psi dx. So this will be equation number 2. Now, if psi is a normalized wave function, remember, if psi is a normalized wave function, the denominator of the above equation, this denominator, is equal to the probability that the particle exists somewhere between x is equal to minus infinity to plus infinity, okay, and therefore has the value 1. So this will be equal to 1, okay. Thus, the expectation value will be given by minus infinity to plus infinity psi asterisk x psi dx. So this will be equal to 1 for the normalized wave function. So this will become equation number 3. Similarly, this could be, for expectation value of the position vector r, okay, it could be written like this: minus infinity to infinity, or simply integration sign, you can put in signs psi asterisk r psi d tau. So this will be equation number 4. In general, the quantity appearing in place of x will be the operator, okay, and is written in the typical form, which is given by equation 3. And okay, so the expectation value of the potential energy now. So this is the expectation value of x position. Actually, the expectation of the potential energy V, it could be written like this will be equal to psi asterisk into V r comma t into this is psi asterisk, so here you will have psi d tau. So this will be question number 5. Okay, now since we know that E is equal to P square by 2m plus V, we can write expectation value E is equal to P square by 2m, okay, plus V, which in terms of the differential operator P, for the differential operator P, you know that the differential operator P is given by P is equal to minus I h cross del, and E is given by minus, rather I, simply I h cross del by del t. So in the above equation, the above equation means this equation which we discussed just before. We'll substitute this operator and we'll write simply I h cross del by del t equal to minus h cross square by 2m del square plus expectation value of V. So this will be equation 6. Now the multiply, what we can do is that we can use the Schrodinger equation, okay. So we just multiply the Schrodinger equation by psi asterisk, and integrating all over the space we can obtain. So we'll just write the Schrodinger equation I h cross del psi by del t into d tau. We are multiplying the left hand side with psi asterisk, the psi asterisk equal to, and integrating it as just I mentioned, again psi asterisk minus h cross square by 2m del square psi d tau plus psi asterisk V psi d tau. This is equation number 7. What we can see over here is that the last term, this last term, it represent, okay, V, simply V, okay. So if this is equation number 7, so from the equation number 5, 6 and 7, it would be consistent only if we assume that the method of finding expectation value of a quantity is to replace it by its operator representation, operate it on psi, and multiply from the left by psi asterisk and then integrate. So this is the basic method. So just say, for example, we have to find the expectation value of E. So the operator is I h cross del by del t. So we'll put psi over here and then we'll multiply with psi asterisk with integration d tau. So this becomes the expectation value of E. So it's very, very simple to remember. Say for example, again we have to find the expectation value of P square by 2m. Okay, so this is for the kinetic energy rather. So what will do is this psi asterisk, the left hand side, the operator minus h cross square by 2m del square, left hand side by right hand side by psi and d tau. So this is the basic method of finding the expectation value for the observable values. Okay, now again continuing further, we need to understand, or we need to find the stationary state. So for that we'll just consider this time dependent Schrodinger equation. Okay, in the case in which the potential energy is not a function of time or is represented by V as a function of R, and it would be given by, so as far as stationary state is concerned, stationary STATIO, and as stationary state is concerned, we'll write the time dependent Schrodinger equation. Okay, that is I H cross del psi as a function of R comma t by del t equal to minus h cross square by 2m del square psi as a function of R comma t plus v as a function of R into psi as a function of R comma t. So this is equation number 1. Now we'll just see if there exists some kind of a solution of the above equation of the form, say psi as a function of R comma t is equal to phi as a function of R and f as a function of t. Now substituting just this equation number 2, substituting this equation number 2 in the above equation and dividing both sides of the resulting equation by the product phi as a function of R and f as a function of t, will obtain I h cross, okay, by f as a function of t dft equal to 1 by phi as a function of R, okay, then minus h cross square by 2m del square phi as a function of R plus v as a function of R, phi as a function of R. So this will be equation number 3. Now since the left hand side of the above equation is a function of time alone here, okay, while the right hand side is a function of space alone, this equality is possible if each of these functions is equal to the same separation constant, and we'll just consider the same separation constant to be, say, E. Okay, so we'll just, okay, setting the left hand side equal to E, we'll get I h cross by f as a function of t dft by dt equal to E, or d as a function of ft by say ft equal to minus I by h cross e dt. Now integrating both sides, okay, integrating both sides, we get ln f as a function of t is equal to minus I by h cross et in fact it's not a function, plus ln f naught, or we'll just get like this f as a function of t is equal to f naught, f as a function of e to the power minus I by h cross, okay, into et. So this will be equation number, say, 4. Now we'll take f0 is equal to 1 or ln f0 equal to 0. In that case, in no loss in generality occurs because ft will always be used in conjunction with phi r to give psi as a function of R comma t equal to phi as a function of R into f as a function of t. And since phi is a function of R, okay, it will contain an arbitrary constant, okay, so or as a multiplying factor, hence ft could be written as e to the power minus I by h cross into et simply, okay. So this will be equation number 5. Now in a similar way, phi r must satisfy this equation, minus h cross square by 2m del square phi as a function of R plus v as a function of R into phi as a function of R is equal to e into phi as a function of R. So this could be written like this, which is equation number, say, 6, okay, which is called time independent Schrodinger equation. And the solution of this Schrodinger equation 1 rather, which we have used earlier, can thus be written as psi as a function of R comma t is equal to phi as a function of R into e to the power minus I by h cross into et. This is equation number 7. Now with the condition that phi r is a solution of equation number this one, that is 6, okay. So the discussion above would show that that the separation constant E introduced earlier is nothing but the energy of the particle. So if we have introduced E, actually it represents energy of the particle. So you can just show it over here, E into psi r comma t. Now I h cross, simply we'll write I h cross del psi as a function of r comma t by del t. It will give you I h cross del, okay, and we'll substitute the value of psi over here, phi as a function of r into E minus I by h cross into into et, okay, by del t. So we'll get E as a function of psi as a function of, so this psi as a function of r comma t. So the position probability density in this particular case, okay, may be written as psi is equal to rho is equal to psi as a function of r comma t mod square, which obviously is equal to phi as a function of r mod square, which shows that at every point r in a space it is independent of time. So this is independent of time. Similarly, the expectation value of all dynamic variables are also evidently time independent. For this very reason, wave function of the form which we have done earlier, psi as a function of r comma t, okay, we have already find it out here, rather phi r into e to the power minus here already we have shown earlier, okay, this one equation number 7, okay. So are said to be represented stationary state. Now this variable, for this variable reason, a wave function of the form this are said to be represented stationary state, okay, or a system described by the wave equation. This one, this particular equation can be represented as a represent a stationary state, okay. So this is the final outcome of this lecture. Next lecture will start the application part of the Schrodinger equation. Thank you.